Glad to see you all in here. So yeah, the title of my talk is Recent Developments in Fully Numerical Electronic Structure Calculation. So this is a field I've been working on for about 6 years now. So I thought that I would actually give you a little bit of an introduction to this field. So I start out by acknowledging my group because I otherwise will forget to do that. I have started recently a group in Helsinki. I've been getting a pretty good funding, so now I have like five students and spending a lot of time managing the group now. But okay, let me get started with the talk because we're behind our schedule. So what we want to do is solve the Schrödinger equation on the computer, and so this is my main interest. So how do we solve this? Okay, so we somehow need to put this on a computer, right? And now the key thing is that we need to discretize the equation. So you cannot put an infinity on a computer. So you have to have a finite number of degrees of freedom, and this is the question of discretization. So what most quantum chemists do is they use Gaussian basis sets. So you take your these one particle functions, which we call the orbitals, and you write them as a linear combination of these atomic centered basis functions that we call atomic orbitals. So they might not be real atomic orbitals. They might also be just something that sort of look like atomic orbitals. So this is why people use these Gaussian functions, even though they are nothing like solutions to the atomic Schrödinger equation. But still, it turns out that once you just put enough of them, then you have enough variational flexibility that you can get something that really looks like chemistry. So basically the point here is that if you look at this ansatz, it doesn't require that these basis functions be atomic orbitals. You can put in whatever, and as long as you have enough variational flexibility, then you can converge your solution. So the trick is that you don't need to, like, if you know chemistry, quantum chemistry in a Gaussian basis, all the same concepts, they also apply when you choose your basis functions differently. You still have Fock matrices, you still have density matrices, you can still do all the SCF convergence acceleration in the same way, provided some limitations. So what are these limitations? So first, let's introduce the finite element method. So instead of using these atomic orbitals, I instead do some discretization in real space. So I can, for instance, if I have 3 dimensions, I can describe the behavior of my orbitals in each dimension in terms of these finite element expansions. So I cut each dimension into segments called elements, and then I put in a polynomial basis within each element. And so then there's a nifty trick that you can use to make your description continuous. So I don't get in that detail, but it's quite straightforward. It's discussed in my papers. And then these Lagrange interpolating polynomials, these have this nifty property that they are defined in terms of these control points, psi I. And then if you evaluate the ith function at the jth node, this is a Kronecker delta function. So basically, when you write any function in terms of these guys, the value of that function at the ith node is just given by the expansion coefficient of the ith function. So these are really nice for practical purposes. Okay, so I use this kind of an expansion in one dimension, and then I can just do that in many dimensions. So these are what these functions look like. So you see that this is like this Kronecker delta property. All the other ones are 0. And then here's a thing I like to mention, because this I did not know until I went to a meeting and was told by a Russian origin mathematician that what I'm doing is wrong. So basically, yeah, don't use uniformly placed nodes, use nodes from quadrature rules, because then this, if you do this, your construction is going to be numerically stable to very high orders. And this is actually really important for the future. So basically, so the finite element method is just a method where you approximate your unknown function as an interpolation. So you have these sets of control points, and then you have these interpolating polynomials. And now this turns your integral differential equations into algebraic equations. So now your degrees of freedom, so the unknowns, they're the values of the function at these expansion points. And the accuracy of your expansion, this is now determined by the numerical order of your polynomials, and then the number of elements, or how you place these elements. And then if you look at what is the error term for this approximation, so it's essentially the n plus first derivative of your function. So this is like how much curvature your function has. And then this is my discretization length. And you see that this guy is very nonlinear. And I will have, in 12 slides, I will have a demonstration which really shows that you should go to very high order, because that's basically a free lunch. Okay, so now we go to the higher dimensions. So this is how you can do one dimension, and then if you just write your basis as a tensor product of basis functions in each of the dimensions, you know, this is quite trivial to do. But the problem is now you get the curse of dimensionality. So if I have 100 basis functions per dimension in 3 dimensions, I will have 1 million basis functions. And now the problem becomes that actually, you know, what I told you before, that you know, like the same concepts apply. You can have Fock matrices and density matrices. You're not going to store like a million times million matrix. So yeah, like forget about it. So basically, this is why in 3 dimensions, you actually need to completely change your algorithms. So this is why historically people use like these iterative schemes. And I will mention a bit later that now there are these integral equation approaches that you don't need to diagonalize the Fock matrix to get the orbitals. But yeah, we'll get to that later. So more recently, there's been development into these multi-resolution wavelets. So the idea is basically to skip this, so you can actually tailor your basis for each orbital. So you only put degrees of freedom where they are needed, and then there's a number of people working on these approaches for 3D case. So Robert Harrison, Greg Belkin, Ed Valeev, Florian Bischoff, Luca Frediani, Stig Jensen, and so on. They have developed these methodologies in recent years that you can actually do fully numerical Hartree-Fock and DFT on moderate-sized molecules. So you can converge to sub-micro Hartree accuracy, some molecules of, I don't know, like 20 atoms maybe. So not like tiny. And that's just because you basically have to reinvent the way in which you do these calculations. So you don't diagonalize Fock matrix, you dress it up as integral equation, and then you can solve basically directly the update for the orbitals using numerical quadrature. Yeah, so this paper is what I like to cite, because this is the first one that actually did this for a number of molecules, and yeah, Luca Frediani's group, they have published a fair number of papers on DFT applied to you know, multi-resolution. Okay, so recent developments. So Frediani, Harrison, and Valeev, like they have done relativistic calculations. Valeev and Harrison did complete active space recently, very recently. So it turns out that you can also dress that up as a integral equation and use the Helmholtz kernel to calculate your orbitals. There's been very recent work for geometry optimization with multi-wavelets. And so there's clearly promise in these 3D approaches. But these are the reasons so why I have not entered that field. Because, well, first of all, there was already competition. The second issue is that you don't have this like systemic error cancellation that you have in atomic orbital basis sets. So in atomic orbital basis sets, you know, your total energy might be wrong by Hartree, but still your relative energies are really nice. Then we know that we need to go to high order coupled cluster theory to get really accurate reaction energies. And then so far, these fully numerical approaches are limited to MP2. So it really, like, this dimensional explosion becomes really hard when you're trying to do correlated methods, because you have lots and lots of virtual orbitals. So the DFT calculations I mentioned, they're still limited to some general gradient approximations, and they're hybrids. So they haven't done any meta GGAs. And then also, if you're trying to do some like tricky systems like diatomics, so if you especially look at transition metals, you have lots and lots of degenerate states or nearly degenerate states that are only differ by symmetry. So it's really important to have precise control over symmetry. So yeah, even though there's a long history of calculations on atoms and diatomic molecules with fully numerical methods. So atoms, like, I don't know, like 50s, 60s, and diatomics from 70s, 80s. So a lot of work was done then, but then, yeah, like 2017, 2018, I realized that, yeah, it might be a good time to revisit this because we have better computer algorithms, we have better computers, the math has developed, so maybe there's some new stuff that could be done. And basically, you know, these systems are really interesting because we have these special coordinate systems that eliminate the nuclear cusp, which is the main problem in most electron structure discretizations. So like in the 3D approaches, you need to refine and refine and refine the spatial representation of the wave function close to the nuclei, because that's where most of the energy sits, and you have like a very, very rapidly changing wave function. But then, so for atoms and diatomic molecules, the coordinate system basically kills away these cusps. And so you have your job for the building up the representation is quite easy, and you can so these very precise calculations have been done since like the 80s for like these diatomic molecules. And also then you can use the symmetry to reduce the dimensionality and still use these LCAO type algorithms. Okay, so my primary motivation sort of is to go through numerical atomic orbitals. So these have been used also for like 4 decades. But basically the problem is that all of the existing implementations, they use very old mathematical methods. So they don't use these high order methods that give you much better accuracy for the same number of degrees of freedom. I will show that 100 functions is enough, while the older ones might use tens or hundreds of thousands of points in the radial dimension. And then using this technology, I think that we can build up much better approaches for then molecular calculations with numerical atomic orbital basis sets. And then the second motivation I had was that because I've been working in density functional theory for a while, so these atoms and diatomic molecules, so when you can write a really precise numerical solver that is cheap, then you can really test and you know, torture these density functionals and see how they behave. So this had been an open issue. So because the full I mean these multi-wavelet studies had not looked at meta-GGAs. All right. So basically, if you want a density functional to be useful in a fully numerical calculation, so you basically can write down three criteria. So you know, when I run a self-consistent field calculation, I start from some guess, and then I relax the density, and then I have some converged density in my basis, and then I make the basis bigger and bigger, and I run SCF, and I should find that the energy does not change. So I should be able to evaluate the energy very precisely for my guess density. I should have a stable SCF and get a very stable energy, and then once I go bigger and bigger, I should find at some point that the energy is not changing anymore. But so yeah, in this study in 2022, which was motivated by the failures I saw in my atomic calculations in finite elements, that things didn't work, and actually you could trace it back to the first step. So if you just use a fixed atomic density, there's many functionals that don't allow you to calculate the exchange correlation energy by quadrature to a precise manner, just using the technology that is already used in all the atomic basis codes. Like every Gaussian basis code uses the same quadrature technology we used in this paper, and so this is really important. Another thing we have pointed out that is that now, you know, you're doing fully numerical calculation, you're converging the total energy to sub-microhartree. Now it becomes a really important question of what is the density functional. So we pointed out in this paper that there are actually many implementations. So you have the same functional, but then it's been described ambiguously in the literature. So for instance, it might be that like, you know, the PBE paper, there's like three choices you can make for the constants for the PBE exchange functional, because the paper gives approximate values, you know, at some points in the paper. And then yeah, you need to really be careful. Like if you're trying to study the accuracy of a Gaussian basis set, for instance, by comparing to a fully numerical calculation, if the functional is not exactly the same, it might be that the error you get is actually from the density functional, it's not from the basis set. All right, so this issue has been solved by our libxc library that I've been developing for over 10 years. And the point is that it's reusable. So this is what I've been working on a lot recently. So it's not the topic of this talk, but reusable software is what I'm a big proponent of. And libxc has shown that this is actually the way to go. So libxc is used in over 40 programs. So ranging from free and open source, academic and commercial ones. So like programs like MolPro, Orca, TurboMol, like these all use libxc. So there is really a way for us to eliminate duplicate code. You know, like maintaining a single implementation takes much less effort than maintaining 40 duplicate implementations. This is just how it should go. All right. So my program is called Helfem. So it's free and open source. You can get it on GitHub. And these are the first two papers where I describe the finite element implementation for atoms and diatomic molecules. So I'm going to briefly talk about how it goes for atoms due to lack of time. So basically, here are my piecewise polynomial basis functions. You divide them by r. This is like established trick in the literature. This just makes it converge way faster. And basically, then I have a tensor product with the spherical harmonics. So I use the same radial basis functions regardless of the angular momentum. So the S, P, D, F, whatever, they all use the same radial basis, and this works perfectly. So it's just that the implementation becomes simpler when you do this. So you could use a different radial basis for the different angular momenta, but this is just for simplicity. So now if you do some math, so I will show that I will have around 100 radial basis functions, and that will give me non-Hartree convergence. But now, you know, you have two L plus one angular functions. This is the magnetic quantum number m for every angular moment in L. And now if you sum this up to a maximum angular momentum of capital L, you have L plus one squared functions. And so if you have up to f functions, then you have a prefactor of 16. So 16 times 100, that's 1600. So this is small. This is tiny. So I can go 10 times higher. If I had 16,000 basis functions, I could still fit everything in core. I could still diagonalize. I can still have a full set of virtual orbitals. So this is great. Okay. So the way I choose my radial discretization. So I came up with this new formula. So I have a uniform grid. It does not depend on the atom. So I have just like this one adjustable parameter p, and then by scanning p from 0.5 to 4 with different numbers of elements. So I have 5, 10, 20, 40, 80, and 160. So I fixed this parameter to be 2. Which gave like really good accuracy here. Note this is logarithmic, 10 to the minus 10, 10 to the minus 8, 10 to the minus 6, 10 to the minus 4, 10 to the minus 2, 1. So like these are like gigantic changes. Okay, so this is with 6 node elements. I fixed my radial grid, and now I look at the order for the elements. This is again logarithmic. So you see, this is for krypton. I flat out here because I'm comparing to a literature value for the total energy that's been given at finite precision. So this is the round-off error from that finite value. So I'm converged with 70 radial functions, provided I use a high order nodes. So here, this is now the effect of your error term of the Lagrange interpolation. So yeah, the takeaway is that 100 functions is enough. So then in these two papers I described, so now when we do the DFT, I'm going to study these functionals. I can just like assume that the density is spherically symmetric, and then I get some simplifications in my equations, and then I can do atomic calculations in a matter of seconds on a laptop. And the trick with meta-GGAs is that now they actually are dependent on the local kinetic energy density, which is the first derivative of the wave function. Unfortunately, the Lagrange interpolating polynomials do not guarantee that the derivative is continuous. So in this paper, I looked at Hermite interpolating polynomials where you basically also force the derivative to be continuous. So how does this work? So if we do the hydrogen atom, we see that actually even the Lagrange interpolating polynomials give me the exact tau and the exact Laplacian when I'm doing Hartree-Fock. So Hartree-Fock does not take tau or the Laplacian of the density as an input variable. This is just a variational theorem forcing the wave function to be continuous, because a discontinuous tau or discontinuous Laplacian would mean that I pay a penalty in the kinetic energy. So the numerical approach works. Now we do Minnesota functionals, and we see that we have these like huge cusps. So kinks and cusps, and like many of them fail even for the hydrogen atom, and this is just proof that they are seriously overfitted. So you have like really pathological behavior. All right, and then in this other paper I already referenced above, I did some like more functionals. So these Minnesota functionals worked sort of for the hydrogen atom, and then I see that again I see failures in converging to complete basis set, or failures in completing converging to self-consistent field equations. But then yeah, there's also like a bunch of other functionals where I had no problems. So these ones should be good to use in fully numerical calculations once the 3D approaches develop meta-GGA support. All right, so I'm at the end. I went a little bit fast. So yeah, key takeaways. So density functionals are not traditionally reproducible. So the original papers, they often do not give data that would allow you to check if your implementation is correct. Like, because this, you need to check to micro-Hartree or sub-micro-Hartree precision. And this is a constant struggle in maintaining libxc, is that new functionals pop out and then there's still not reference data. So the solution for this reproducibility is just to use libxc, because then you know that the functional is going to be the same regardless of the program you use. The numerical behavior density functionals has not been studied adequately. So this is what we showed in 2022. So with the fixed atomic densities, and then what my work on the finite element approaches showed. So basically, a functional should be smooth enough to work than in an atomic, basis program, because this number of quadrature points, there's a default value for this. But if you run calculations, you should check that it's actually sufficient. So the default for everything might not be good for the functional you use. So caveat emptor. And yeah, so these fully numerical calculations are now tractable for moderate sized molecules. And in HelFem, you can do atoms and diatomic molecules quite easily. So basically, these old codes existed, but they are really, really hard to use and set up. And the beauty of HelFem is that you can run it like a Gaussian basis calculation. So you just give it the atom and things like this, and it will do the initial guesses and so on automatically. All right, so what was mentioned in the first previous talk. So we have a satellite meeting in Helsinki next summer for reusable libraries in quantum chemistry. So the topic I was just talking about. So I do not see the point in having everyone reinvent the wheel. I want to have people talk more, amongst each other. Is there potential for different codes sharing the same implementation of a given topic? So I don't know, like a couple cluster module, things like this. So the main purpose is just to get the developers of various quantum chemistry packages and various libraries. So anyone interested, come in. So we're going to be situated at the seashore, far from everything, at a conference center with full room and board. The registration and housing is going to be less than 1,000 euro per person. So there's going to be lots of time for discussion and poster sessions. So yeah, like it's going to be single room conference around 100 people. And yeah, these are my acknowledgements. Thank you, and welcome any questions.
Thank you very much. Thank you very much. We have time for one or two quick questions.
Very nice talk. About the, you use the phrase moderately sized, so I just want to understand here. Moderate means, you can do atoms and diatomics now. Are we still going to face the issue of the multi-resolution picture that you were talking about in the beginning, or did I miss it? How does one extend this? Is it obvious?
No, so basically, like at the beginning, I talked about the multi-resolution things, and so that's not what I work on personally.
Yeah.
So I'm not sure on what size they can actually do.
Okay.
So the thing about these multi-resolution approaches is that they're actually really nicely parallelizable. So if you have a big computer, you can run systems, and so everything depends on what precision and so on and so forth. But yeah, like there's been studies of like transition metal ligands, for instance. So it's like it's at a stage where you can actually use it for studying like chemical things. But like to me, it's still that, you know, like it's not going to replace, like the multi-resolution stuff is not going to replace Gaussian-based technology.
Yeah, so what do you anticipate as far as how far you'll be able to go, let's say?
I'm sorry?
How far will you be able to go, which is your guess?
So I haven't written the NAO-based code yet, so I'm still, you know, working through the basic technology, and because of, you know, like what I talked about, the reusability, I don't want to write a new monolith. I want to have like this, you know, I want to have this like rich ecology of these reusable libraries that I can, you know, like that I don't need to write these for my program. I could just use the same as everyone else, because this is the way to also make it then fast. So there are, you know, codes like FHI aims and DMOL and so on and so forth. So the numerical atomic orbitals, you can really make them scale really big, because the representation is sparse when you go to big systems, which Gaussians are not, because Gaussians are, you know, like they have global support. NAOs have finite support, so you know that it's going to be a hard zero when two atoms are more than practical infinity away from each other.